All right, today we're going to talk about series and convergence. So being that this is our first discussion on the subject, we're going to talk about some of the basics and work our way forward. All right, we're going to start to understand the idea of a convergent infinite series. We'll talk a little bit about geometric series and what makes it convergent or divergent, as well as the nth-term test for divergence, which is typically the first test we use for an infinite series, the first test I use. An infinite series. Any series that goes from 1 to infinity is considered an infinite series. You would have a never-ending series of summations that could go to a single number or could go to infinity. All right, in an effort to add up an infinite series, very often we'll use what we call a partial sum. So for example, S sub 3, we'll take the first 3 terms, add them up. For S sub 5, we'll take the first 5 terms and add them up. The sequence of partial sums very often will tell us if a series is going to converge or potentially diverge. All right? So, a series converges if it heads towards a real number. If the partial sum does not head towards a real number, heads towards infinity, this series will diverge. So, for example, the partial sum, S1 is 1/2, right? S2 is 1/2 plus 1/4, which is 3/4, right? What's my third partial sum? Which would be 7/8. My fourth partial sum, fifth partial sum, so on and so forth, would be getting ever closer and closer to the number 1. So therefore, we would say that this series is convergent and its sum is 1. All right, let's take a look at the next one. The next one we have this series here. So I'm going to start labeling some of the partial sums. I have a few here for you. And what do we notice in this series? We notice I've got a negative 1/2 and a positive 1/2. They add up to 0. I've got a negative 1/3 and a positive 1/3. They add up to 0. I'm going to have a negative 1/4 and positive 1/4. They're going to add up to 0. So all the subsequent terms after the 1 are basically going to be eliminated because they're going to be added and subtracted the same thing. So this series again would converge and its sum would be 1. What about this series here? Right? My partial sums, I got 1, then 2, then 3, then 4, then 5, then 6, so on and so forth. I would say this series diverges because it doesn't head towards a single real number. It will continually head towards infinity. All right, the series that we saw earlier, where we had these terms that canceled out, very often is called a telescoping series. And it's a telescoping series because you're focused further and further out on the number 1. Telescoping series is typically convergent. All right, so let's see. Geometric series, all right. Geometric series is of the form a times r to the n. So for example, this particular series, I've got 1 times 1/2 to the n power. Right? And that would put it in the form of a geometric series. My a would equal 1. My r would equal 1/2. All right? As long as r doesn't equal 0, it is a geometric series. A geometric series diverges when r is greater than or equal to 1. Notice the absolute value of r. All right? It is convergent when when the absolute value of r is in between 0 and 1. If it's convergent, you can use this to get the sum of your series. So for example, this series right here, my A equals 3, my R equals 1/2. So what conclusion can we make about convergence or divergence? We can make the conclusion that the absolute value of R is in between 0 and 1. Therefore, it is convergent. And what I'd like you to do right now is pause the video and get the sum of the series. Okay, if you pause the video, you would see that I've used A over 1 minus R. Get 3 over 1 minus 1/2, which would equal indeed 6. Here's another geometric series. My common ratio, my R, is 3/2. Since it is greater than or equal to 1, the series must diverge. If the series diverges, you don't want to get a sum. Sum is infinite. Here are some properties of series. These properties are very similar to properties we used for limits. I'm not going to necessarily harp on these a lot, but you should keep these in mind. All right. I do want to get into the nth-term test for divergence. Very often the nth-term test is used. It's the most general test for divergence, and I typically will use it first on any series that I'm testing for convergence divergence, because if it's true, it's a very quick and easy way to test for divergence. So it is usually my first shot. All right, so the limit of the nth term of a convergent series says if the series converges, then the limit as n approaches infinity is going to be 0. The contrapositive gives the test for divergence. Basically what it says is that if n approaches infinity and the limit is not 0, then it diverges. And this is the test right here. Okay? All the upper thing is saying is that series that converges, the limit's going to be 0, but it's not always that way. All right? So you could have a series that diverges where the limit would be 0 as well. So this really doesn't tell you, gives you really no information as to convergence or divergence. All right. So 2 to the n. If I take the limit as n approaches infinity, it equals infinity. Therefore, it's not 0. The series diverges. Very quick and easy. All right, the next series here, take the limit as n approaches infinity. Got to use L'Hopital's rule, but it equals 1/2. Therefore, you would say the nth term is not 0. Therefore, the series diverges. All right. However, if we have 1 over n, the limit as n approaches infinity is 0, correct? If it is 0, the nth term test does not apply, and we can't draw any conclusions about convergence or divergence. All right, this was a very quick introduction to convergence and divergence. Talked to you about the geometric series, a little bit about how to recognize a telescoping series, as well as the nth term test. These should all be looked at before you go into the more complex things. So I hope you enjoyed it, and I'll see you on the back end.